Hello friends, this is Dharmin Patel. Welcome to the lecture series of Mathematics 2. In this lecture, we will discuss the methods of reduction of order for higher order homogeneous linear differential equation. In the previous lecture, we studied how to find the general solution for higher order ordinary homogeneous linear differential equation when auxiliary roots are distinct, but when some roots are repeated or same, then how to find the solution we will see in this lecture. First of all, we revise the last topics: higher order homogeneous linear ordinary differential equation with constant coefficient. The equation of the form fn d raised to ny by dx raised to n plus fn minus 1 d raised to ny by dx raised to n minus 1 up to f2 d square y by dx square plus f1 dy by dx plus f0 y equal to 0 is called higher order ordinary differential equation homogeneous case because RHS is 0. Here f1, f2, fn are some constant. To solve this type of differential equation, we will take the differential operator d by dx equal to d. Then our equation becomes fn d raised to ny plus fn minus 1 d raised to n minus 1 y plus f2 d square y plus f dy equal to 0. After that, we common the y, then our differential equation is fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d plus f0 y equal to 0. Here y is not equal to 0, so fn d raised to n plus fn minus 1 d raised to n minus 1 plus f2 d square plus f1 d plus f0 is 0. It is known as auxiliary equation for our differential equation. Now, after factorizing this auxiliary equation, we get the some linear factors d minus m1, d minus m2 up to d minus mn equal to 0. Therefore, m1, m2, m3 up to mn are auxiliary roots for our original differential equation number 1, and our solution is also depends on these auxiliary roots. Let us see the general solution of the higher order homogeneous linear differential equation. Here our differential equation is of this type: d raised to n plus fn minus 1 d raised to n minus 1 up to f0 into y equal to 0. After taking y not equal to 0, then fn d raised to n plus fn minus 1 d raised to n minus 1 up to f2 d square plus f1 d plus f0 y f0 equal to 0. It is auxiliary equation, and after factorize we get the some linear factors, and the solution of this factors is known as the auxiliary roots. Now our general solution of the homogeneous differential equation is depends on auxiliary roots m1, m2, mn, and how to find it. Here our particular solution of differential equation 2 is related to auxiliary root m1 obtained as d minus m1y equal to 0. That can be rewrite as dy by dx minus m1y equal to 0. Also it can be written as dy by dx equal to m1y, which is our first degree ordinary differential equation. We know the some methods to solve it. Here we solve by separable variable method, then we get 1 upon y dy equal to m1 dx. After taking the integration and solving this, we get y equal to c1 e raised to m1x, which is our particular solution of the differential equation number 1. Similarly, we can find the other particular solutions which are as y equal to c2 e raised to m2x from the second factor, y equal to c3 e raised to m3x from the third factor, up to so on, and finally we get the y equal to cn e raised to mnx from the last factor. Here this method is applicable when all the auxiliary roots are different. Let us revise some examples related to this. Here example is d square y by dx square plus 5 dy by dx minus 6y equal to 0. That can be rewritten as d square y plus 5 dy minus 6y equal to 0, where d is dy dx, and auxiliary equation becomes d square plus 5d minus 6 equal to 0. After factorize we get the factors of auxiliary equation. Here d plus 6 and d minus 1 equal to 0, and auxiliary roots are m1 equal to minus 6 and m2 equal to 1, and therefore our particular solutions according to the auxiliary roots are y1 equal to e raised to minus 6x and y2 equal to e raised to x. Therefore, we have a general solution which is known as complementary function, and it is denoted as yc will be c1 e raised to minus 6x and c2 e raised to x. Here y1 equal to e raised to minus 6x and y2 equal to e raised to x are particular solution of our differential equation d square y by dx square plus 5 dy by dx minus 6y equal to 0. But we have to check here they are different from each other or not. So we have to check the linearly independentness of our functions e raised to minus 6x and e raised to x. In this case, we will use the Wronskian determinant to check the linearly independentness of our particular solutions y1, y2, y3 up to so on. Here, to check linearly independentness of y1 and y2. y1 is e raised to minus 6x and y2 is e raised to x. So our Wronskian determinant is y1, y2, y1 dash, y2 dash not equal to 0, then a y1 and y2 are linearly independent. If this determinant is 0, then y1 and y2 are linearly dependent. Here put the y1 and y2 in the Wronskian determinant, which is y1, y2, y1 dash, y2 dash. That means in the first row we are writing y1 and y2, that is e raised to minus 6x and e raised to x. In the second row we are putting the derivative of that means minus 6 e raised to minus 6x and e raised to x. After solving this determinant, we get the 7 times e raised to minus 5x, which is never 0. So y1 and y2 are linearly independent. Here m1 and m2 are different. So we can easily find out that these are linearly independent solution. But when we have a auxiliary roots are same, that means m1 is repeated or m2 is repeated in the second order differential equation, then how to find the second solution? So for that we will use the method of reduction of order for higher order homogeneous linear differential equation. Here this method is applicable when we know the one solution of the differential equation and second solution should be linearly independent with the first one. Here we will solve for the second order linear differential equation. Here f2 d square y by dx square plus f1 dy by dx plus f0 y equal to 0 be a second order homogeneous linear differential equation. That can be rewrite as d square y by dx square plus f1 by f2 dy by dx plus f1 by f2 y equal to 0. Here we divide the whole equation with f2, then we get d square y by dx square plus px dy by dx plus qx y equal to 0 form of the differential equation. Here we are taking f1 upon f2 equal to px, it is a function of x, and f0 upon f2 is equal to qx, it is also a function of x. Here f1, f2, f0 are also a function of x. Now we know the one solution of our differential equation which is known as y1. Therefore second solution is obtained like this: y2 equal to y1 into integration of 1 upon y1 square into e raised to integration of px dx, and then we are taking the integration of that part and it is multiplied with y1, and finally we get the linearly independent solution. Verify here y1 and y2 are linearly independent by Wronskian determinant. Let us see some example related to this. Here our differential equation is x square d square y by dx square minus 3x dy by dx plus 4y, and one solution is x square. Here one solution is x square. We can check by putting y double dash y dash in differential equation. We get the right hand side will be 0. Now here one solution is known, so we can rewrite this equation x square y double dash minus 3x y dash plus 4y equal to 0 as, after dividing by x square we get y double dash minus 3x by x square y dash plus 4 by 3x y equal to 0. Now compare this equation with the differential equation d square y by dx square plus px dy by dx plus qx y equal to 0. Then our px equal to 3 upon minus 3 upon x and qx is 4 by x. Here y1 is known solution, then Our second solution is obtained like this: y2 equal to y1 into integration of 1 upon y1 square into e raised to minus integration of px dx. Then we find the solution like this using this formula: y2 equal to y1 into integration of 1 upon y1 square into e raised to minus px integration of px dx into dx. Now we have a px is minus 3 by x and y1 equal to x square. Then we will put in this formula. Then we get y2 equal to x square into integration of 1 upon x square square into e raised to minus integration of minus 3 by x dx into dx. Here we know the integration of 3 by x, so we get finally y2 equal to x square into integration of 1 upon x raised to 4 into e raised to 3 log x dx. And then finally we get x square into integration of 1 upon x square square into e raised to log x cube, that can be written as only x cube. Finally we get y2 equal to x square into integration of 1 upon x raised to 4 into x cube. That means we get finally y2 equal to x square into integration of 1 upon x, that is log x. So finally we have a solution x square log x, which is our second solution. Now we will check the linearly dependent or independent solutions. First of all, we use the Wronskian determinant, which is y1, y2, y1 dash, y2 dash. If it is not equal to 0, then our functions are linearly independent. Here we put the value of y1 and y2 in the Wronskian determinant. In the second row we are writing the derivative of y1 and y2. After solving that, we get the only x cube, and x is not equal to 0, therefore x cube is not equal to 0. That means y1 x square and y2 x square log x are linearly independent solution of our differential equation. Here this method is very useful when we know the one solution, and we find the second solution by method of reduction of order, and its formula is y2 equal to y1 into integration of 1 upon y1 square into e raised to minus integration of px dx into dx. That means method of reduction of order is applicable when we know the one solution of second order homogeneous linear differential equation. Also it is applicable when our second order homogeneous linear differential equation have a same repeated roots. Now in the next lecture we will see the types of solution of higher order homogeneous linear differential equation. Thank you very much for watching.